Lagrange interpolation. Finding the one polynomial that passes exactly through a set of data points. Here's the problem we are solving. We are given n plus 1 data pairs with distinct x values. We want a polynomial p of degree at most n that passes exactly through every single one of those points. It turns out a polynomial like this always exists, and for a given node set, it's unique. There's only one. This shows up constantly in thermal engineering. Steam tables, refrigerant tables, they only give you properties at specific tabulated states. Sensor calibration curves are measured at a handful of points too, but in practice we constantly need a value that falls between those points. So here's Lagrange's idea. Instead of solving a big system of equations for the polynomial's coefficients, build P directly as a weighted sum of basis polynomials, one basis polynomials per data point. P sub n of x equals the sum over I of f sub I times L sub I of x. Each L sub I is built from a simple product. L sub I of x is the product over every other node j of x minus x sub j divided by x sub I minus x sub j. The key property, L sub I equals 1 at its own node and 0 at every other node. So in the sum, each term only switches on right at its own data point. The simplest case, linear interpolation, n equals 1. P1 of x equals f0 times x minus x1 over x0 minus x1 plus f1 times x minus x0 over x1 minus x0. This is exactly the two-point linear interpolation you already use every time you read between two rows of a steam table. Add one more point and we get the quadratic case. P2 of x works the same way, extended to 3 points. Each term now has a product of two factors on top and bottom. Let's run the numbers on a simple hand-checkable case. Data, x equals 1, 2, 3 with f equal to 1, 4, 9. That's just x squared. We want to estimate f at x equals 1.5 using the quadratic Lagrange polynomial through all 3 points. Plug x equals 1.5 into each basis polynomial. L0 at 1.5 comes out to cone 375. L1 comes out to cone 75. And L2 comes out to negative 0 cone 5. Here's the same calculation in EES. Build each basis term with the product formula, then sum f times L over all 3 points. And the result, P2 at 1.5 comes out to 2.25, exactly matching 1.5 squared. A quadratic Lagrange polynomial is exact for quadratic data. Away from the nodes, the error follows a predictable pattern. The error is f of x minus p sub n of x equal to the n plus first derivative at some xi divided by n plus 1 factorial times the product of x minus every node. Notice the error is exactly 0 at the nodes themselves. It grows in the intervals between them, and it's usually worst near the ends of the data range. The obvious next move is to just add a lot more points. Intuition says more points should mean a better fit. Let's actually test that with a nastier function. This is Runge's phenomenon. 21 equally spaced nodes on the function, 1 over 1 plus 25x squared, a degree 20 Lagrange polynomial. Look at the edges. The fit doesn't just get worse, it explodes. Max error nearly 60 on a function that only ranges from 0 to 1. It comes down to where the nodes sit. Equally spaced nodes cluster in the interior of the interval, but they're too sparse near the endpoints. To still pass exactly through every single point, a high-degree polynomial has no choice but to oscillate wildly near the edges. One fix, change where the nodes sit. Nothing about the function or the degree 20 polynomial changed. Only the node spacing did, clustered near the endpoints now. The oscillation is gone, max error drops from about 60 down to under 0.2 point. And it's not a one-off, it holds as we keep adding nodes. Max error against node count on a log scale. Equally spaced nodes diverge past about 10 nodes. Chebyshev nodes converge steadily the whole way. So, two ways out of Runge's phenomenon. First, keep a single global polynomial, but choose Chebyshev node placement. Second, and more general, abandon the idea of one global polynomial altogether and stitch together piecewise low-degree pieces instead. That second path is the cubic spline, and that's next in this series.